In this tutorial, you will learn how to describe semantic data, triples, and a triple store, create a MarkLogic database to use as a triple store, create semantic indexes, load RDF data into the MarkLogic triple store, test the triple store database via a REST API, query triples using SPARQL, and query triples using XQuery. In this section, we will define what is semantic data, why it's used, what is RDF, what are triples, and what is a triple store. In the exercise that follows, we will create a MarkLogic triple store, enable indexing of triples in our triple store, create a MarkLogic XDBC application server to load RDF using the MarkLogic Content Pump, and create a REST application server to access our RDF data through REST endpoints. Semantic data enriches query results to provide greater meaning. Search results are combined with other facts for a richer experience. You can combine facts, documents, and values together to gain better insights. Semantic data allows computers to understand information without the help of a human user. For example, if Ted lives in Chicago, Illinois, and Ted lives near Wrigley Baseball Field, and Ted has a roommate named Sam, and Ted and Sam both attend baseball games together, a computer could reason that Sam lives in Chicago, Wrigley Field is in Chicago, Chicago is in Illinois, Ted and Sam both live in the United States, etc. In this example, we are displaying markmail.org, a rich MarkLogic application that pulls in over 90 million open source mail lists, indexes them, and allows anyone to search them. The search term, Hadoop, returns a list of email messages related to the search. The search term is highlighted in the snippets of each of the messages. We also get metadata about each message, including the sender, the date the message was sent, and which message list contained the message. On the left side, we also get facets, more information regarding our search. We can drill down into various aspects of the search results. On top, a chart shows how the search term is trending over time in a particular message list. Starting with an already rich MarkLogic application, the results could be richer. For example, what if the search term could be combined with other known facts about Hadoop? The search could return those facts and add an extra piece of information, an information panel, containing the name of the project, the logo, the project description, key personnel, and other related projects. This information panel could be dynamically created with every search, returning more information about the question you were asking. With even more facts stored, a profile box could be displayed when you hover over the sender's email address, displaying facts about the person, including the person's name, email address, which list he or she commits to, the person's company, etc. Combining search results with facts about the world has yielded more information than was originally expected. In this example, MarkMail is searched with the term affiliation:IBM, returning results if IBM is found in the message or an email address. What if facts about people could also be searched, such that we knew an email message was from someone that works at IBM even though he or she sent the message from his or her personal email? We could then display more results since we would know more facts and could relate them to the original question. Using these facts, Sam Ruby, who was using his personal email address ending in intertwingly.net, would be displayed even though the term IBM is not in the message, since it would be a known fact that Sam Ruby works for IBM. In the first two examples are search applications that are informed by facts about the world. We might also build an application that uses facts about the world informed by searching documents. In this example, we are recruiting Hadoop experts within one time zone of our current location. We'd like to be cost conscious, so we would be very interested in candidates that live in an area with a reasonable cost of living and lower salaries. These facts, areas with a reasonable cost of living that are within one time zone of our location, can be combined with our previous fact-enhanced results of our MarkMail search for Hadoop to display a trend of his or her postings to a particular message list. Semantic data is textual and follows a specific syntax called RDF, or Resource Description Framework. These RDF documents are stored in databases called triple stores. RDF facts are stored as triples. Triples have subject, predicate, and object components. For example, the triple Fred lives in London has the subject Fred, the predicate of lives in, and the object of London. Triples use International Resource Identifiers, known as IRIs, to refer to locations that can define the triple data component, such as what is the meaning of the predicate lives in. These RDF documents are stored in databases called triple stores. Triple store databases in MarkLogic have a special index setting to quickly locate triple data. In this scenario, we will create a new triple store in MarkLogic and configure it. We begin by using MarkLogic to create the database and specify configuration options such as semantic indexing. We also create an XDBC application server so we can load triple data into our triple store using MarkLogic Content Pump in a later exercise. Finally, we create a REST application server for this database. During this interactive section, you will be asked to click on screen elements, enter text or type commands into the command line. You may skip steps by clicking on the forward button. Click the button to begin. We first create a forest for our triple store database. Click on the forest item. Click on the Create tab. For the forest name, type triple-01, then press the Tab key. Click the OK button. Now we create our triple store database. Click on the Databases item. Click on the Create tab. For the database name, type triples, then press the Tab key. Click the OK button. Click the Database Forest link to attach the forest to the database. Click the triple-01 forest to select it. Click OK. We will enable the triples index and also the collection lexicon. The collection lexicon is used and required by the REST API instance that we will create in this exercise. Data ingested into the MarkLogic triple store is indexed to enable faster searches. Click on the triples database. Click on True to enable RDF triple indexing. Click on True to maintain a lexicon of collection URIs. Click the OK button. To load data into a MarkLogic database using MarkLogic Content Pump, or MLCP for short, an XDB server is needed. We chose MLCP as our data loading tool as our data is contained in RDF documents on the file system, and MLCP provides a fast and efficient method of loading data. XDB servers are defined at the group level and are accessible by all hosts within the group. Each XDB server provides access to a specific database and to a library of XQuery programs that reside within a specified directory structure. Click the Groups node. Click the default group. Click on the App Servers node. Click the Create XDBC tab. For the XDBC server name, type 8040-triples-XDBC, then press the Tab key. For the root, type a /, then press the Tab key. For the port, we selected a port number that was currently open. Type 8040, then press the Tab key. We want to use our triples database for this XDBC server. Click the Database drop-down arrow. Select the triples item from the list. Click the OK button. The XDBC server is created and the MarkLogic service is automatically restarted. You have successfully completed this task. Let's explore triples themselves. We will define triples, see an example of a triple, investigate how triple data is gathered, and how to load triples into a MarkLogic triple store. In our exercise, we will load triples into our triple store with the MarkLogic Content Pump, then verify the triples in our triple store. MarkLogic triples are stored in XML documents. Queries in MarkLogic that use the triple index, such as SPARQL queries, don't access the underlying triple document. Triples can be ingested to a MarkLogic triple store using MLCP by using MarkLogic's sem:/rdf-load XQuery function or with a REST endpoint. Triple documents are stored by default within a directory called /triple store. Depending on the MarkLogic tool used to load the triples, another directory could be specified. This is an example of a triple document stored in the MarkLogic triple store. Multiple triples could be within the parent sem:\triples node. Notice the sem:\subject, sem:\predicate, and sem:\object nodes. Triple documents within the MarkLogic triple store are indexed when the triple index setting in the database is enabled. Indexing can be enabled either in the administrative interface on port 8001 or by using the Configure button in the Information Studio application on port 8000. Triple index data is stored compressed on disk. When triple data is needed, it is cached in either the triple cache or the triple value cache. The triple value cache stores uncompressed blocks, so access to data is fast. RDF facts come from a variety of sources. They could be generated already and available for use, such as the Dublin Core that provides a basic vocabulary for describing documents and other content such as videos, books, and artworks, or DBpedia that extracts structured information from Wikipedia and makes this information available on the web. Facts can come from document content, capturing data from XML documents or converting a Word document's table of contents to triples. Facts might originate from metadata in documents, such as the document file type, the author, subject, or version. Metadata from web pages could be converted and stored as triples. In this scenario, you have been asked to load triples regarding person data from a collection of triples from dbpedia.org. We begin by locating the data we want to load from the dbpedia website, then downloading the triples file to a local temp directory. We then use MLCP to load and split the person triples file into the triple store that we created. We also verified that the content has been successfully loaded and stored as specified. The MLCP binary files and triples data file have been extracted for you. A user has been created and assigned the privileges to import the content. During this interactive section, you will be asked to click on screen elements, enter text, or type commands into the command line. You may skip steps by clicking on the forward button. Click the button to begin. The MLCP command has been entered for you. Take a moment to review the command. The import parameter specifies data is to be imported to the database accessible on host localhost, port 8040, which is our XDBC server previously created for our triple store. We're using the username of admin and the password of admin, which must have sufficient rights to read and write data to the triple store. The input file we downloaded from dbpedia.org, persondata_en.nt, has the triples we want to load. There are two modes for MLCP, local or distributed, which is for using MLCP with Hadoop. Since we're not using Hadoop, we have specified local for the mode. The input_file_type parameter specifies the data type to be RDF. This is important when loading triples through MLCP. We're giving our triples a database URI prefix of /people/. Press the Enter key to execute the command. The MLCP output indicates the status of the load, success, and the execution time taken. We will now verify the documents are stored in the triple store by using our REST API interface. Press the Enter key to continue. In a browser, we will navigate to the URL http://localhost:/v1/graphs/things. The port 8321 is the REST API interface port we defined for the triple store previously. Note the v1/graphs/things is a standard HTTP REST endpoint for querying with SPARQL. Without any other parameters, the endpoint returns the first 10,000 triples in the triple store. Enter admin for the username, then press the Tab key. Type admin for the password, then press the Enter key. Up to the first 10,000 triples are displayed in the browser. Click on the link of the first triple regarding Dr. Death, Steve Williams. All of the triples in the triple store that have a subject equal to Dr. Death, Steve Williams, are displayed in the browser window. Information such as Steve Williams' place of death and birthplace are displayed as triples with a reference, an IRI, in the objects to those places. Other information about Steve Williams, such as a description of him, is also displayed. Click the back button in the browser. Click the link for the second person, Teddy. The triples where the subject is equal to Teddy Man is displayed in the browser, including his birthplace and description. You have successfully completed this task. Press the Enter key to continue. SPARQL is the standard query language for data stored in the Resource Description Framework, or RDF, format. In this section, you will learn more about what is SPARQL and how it is used to query triples. In the exercise, you will use MarkLogic's Query Console to query triples using SPARQL and MarkLogic's XQuery sem functions. To query triples in MarkLogic, the following methods can be utilized. Using the REST endpoint of /v1/graphs/SPARQL to pass in a SPARQL query, or by using the REST endpoint of /v1/things followed by the IRI of the desired triple to be returned. You can use XQuery using the sem SPARQL function, CTS triples function, or the CTS triple range query function. Finally, extensions to MarkLogic's search API could also be created. SPARQL queries specify a graph pattern stating what to query for in the underlying dataset. A graph is defined as a triple subject and a triple object linked by a triple predicate. Projected expressions can contain values derived from constants, function calls, or other expressions in a SPARQL select list. They allow other data to be used for columns in the query's result set, such as calculations. Queries can be constrained using filters, limits, or offsets. Queries can be combined with logical ands and ors. There are four basic types of SPARQL queries: select, construct, ask, and describe. We will examine each of the above and also working with IRIs and prefixes. Variables can be declared in SPARQL by prefixing the name of the variable with either a question mark or a $sign. The question mark is the most common method. Variables are only bound once per row of triples returned. Once a variable contains a value, it will always contain that value regardless of the number of times it is used in the SPARQL query. When a new row of triples is accessed from the results of the SPARQL query, the variable will be bound again. The object of a triple can be any type. Use the ** followed by the XML schema type to strongly type a variable or constant. The select specifies the data or columns to be returned. The where clause specifies the data to be searched. There must be a variable bound in the pattern. In this example, the triple graph pattern is returning rows of subjects and predicates where the object is equal to the constant London. The mySubject and myPredicate variables will be bound per row of triples found. However, only the value contained in the myPredicate variable will be returned as a result. Click the Explain This Example button for a walkthrough of this SPARQL query, or press the Enter key to continue. In this example, we are selecting, returning as rows of data, the subject part of a triple bound to a variable called mySubject. Note that the value of mySubject doesn't change for the same row of data found, even though mySubject is used multiple times in the SPARQL query. The variable is only bound once. The where clause is searching for any subject and any predicate, but only if the object part of the triple is equal to London. Click the Run button to see the result. The results returned are rows of subjects from triples stored in our triple store. Note that mySubject is the only column since it was the only item defined in the select. Press the Enter key to return. You can constrain and or reorder the return table of data by using filters, limits, offsets, and order by. Filter can restrict the results by using expressions that must test to true. For example, you might use a regular expression to match a certain pattern in a string. Limit specifies an upper bound for the number of results returned. Offset starts the returned result set at the specified position. Limit and offset can be used together to control the pagination of results. Order by returns a result set in the specified sorted order. By default, results are sorted in alphanumeric order. The period between triple patterns concatenates the two result sets that share one or more part of the triple. In this example, the result set of the first triple pattern, return Danny Kaye's birthplace, is used to establish a relationship with the second triple pattern. Instead of finding all names and all birthplaces in the second result set, only those names that have the same birthplace as the first result set are found. We are returning the rows of subjects from the second pattern as a result. Click the Explain This Example button for a walkthrough of the SPARQL query, or press the Enter key to continue. In this example, we are still returning one subject bound to a variable called subject, but we are using two patterns in the where section of our SPARQL query. The prefixes db: and onto: provide an easy-to-reference namespace to the IRIs for dbpedia.org/ontology and dbpedia.org/resource. These are two references we will use to locate the definition of the person Danny_K and the definition of the predicate birthplace. The first pattern finds Danny Kaye's birthplace and returns the birthplace in the variable we called object. The second pattern finds any subject that has the same birthplace, since the variable called object already has a value from the first pattern. The period at the end of the first pattern indicates we are using multiple patterns. Click the Run button to see the results. The rows of the subject part of the triples that match our where patterns are returned. Since we only asked for the subject to be returned as part of our select, it is the only column displayed. Press the Enter key to return. A semicolon can be used between triple patterns to specify the following pattern uses the same subject as the previous pattern. For the pattern following the semicolon, you would only need to specify a predicate and an object. In this example, we are returning subject IRIs, full names, and last names where the predicate, called description, matches the object value of author. We are returning the result set sorted by last name descending, and returning the first 10 rows. Click the Explain This Example button for a walkthrough of this SPARQL query, or press the Enter key to continue. We are using prefixes to refer to two resources. The first, DC:, refers to the open resource Dublin Core, which contains metadata about works in print and art as well as other topics. The second prefix, FOAF:, refers to friend of a friend that contains metadata about people, including their names, email addresses, etc. We will use the first prefix to define our use of the predicate description, and use a second prefix to define our use of the predicates name and surname. We are now selecting three columns to be returned: author, fname, and lname. We are matching the pattern where the author subject IRI is returned from a predicate IRI of description, and matching objects with the string value of author. We are also using two more patterns, each reusing the same subject as the first pattern. We are using the semicolon to indicate that these patterns share the same subject. The second pattern locates the full name of the author and binds it to the variable fname as the object using the predicate name. The third pattern locates the last name of the author and binds it to the variable lname as the object using the predicate surname. We are ordering the rows returned by the last name in descending order and limiting the number of rows returned to the first 10. Click the Run button to see the results. The three columns are returned. Author contain the subject IRI of the triple, fname contain the author's full name, and lname contain the author's last name, both from the object part of the triple. The results are returned in last name descending order. Press the Enter key to return. The union clause does an OR between multiple patterns. The example returns all names of people that were either born in the same place as Danny Kaye or died in Washington, D.C. Click the Explain This Example button for a walkthrough of this SPARQL query, or press Enter key to continue. In this example, we will extend our Danny Kaye example to also use union followed by another pattern. As in our original Danny Kaye example, we are returning the subject part of the triples found in a variable called subject. In our original Danny Kaye example, we returned Danny Kaye's birthplace, then searched for any subject IRI that shared that birthplace. We are now also going to union those results with subjects that had a death place of Washington, D.C. The results returned will be all subject IRIs that either were born in Danny Kaye's birthplace or who passed away in Washington, D.C. Click the Run button to see the results. The results are similar to the results for our Danny Kaye birthplace example, except the subject IRIs would also include those that passed away in Washington, D.C. as well. Press the Enter key to return. The four types of SPARQL queries are Select, which returns a result set based upon matching query patterns; Construct, that returns triples according to the specified pattern; Ask, which returns a yes or no response to the specified pattern; and Describe, which extracts an RDF graph describing a list of resources or variables being sent. Describe is useful when there is not enough information known to query about a resource. IRIs are like URLs, but can contain Unicode characters. IRIs are used for subjects and predicates. Objects can be any type, including an IRI. In MarkLogic SPARQL queries, the subject and/or the object can be the URI of data in a MarkLogic database. The prefix clause can be used to create shortcuts to IRIs, as they can sometimes be very long. In this example, two prefixes are defined. The first, with a namespace of DC:, refers to the IRI http://perl.org/dc/elements/1.1/. This references the Dublin Core metadata terms, a set of vocabulary terms used to describe a full range of web resources such as video, images, and web pages, and also physical resources such as books and objects like artwork. The second prefix, with a namespace of FOAF: refers to the IRI http://xmlns.com/FOAF/0.1/. This references the friend of a friend ontology that describes people, their activities, and their relations to other people and objects. Anyone can add his or her entry to the ontology. In MarkLogic, SPARQL select queries return a sequence of map objects. Each map is a set of bindings that satisfy the query. The returned results from construct and describe queries are sem:/triple values. SPARQL ask queries return a single Xschema Boolean value. Results that are returned can be serialized to other formats, such as XML or JSON. RDF formatted results can be serialized to triples, quads, turtle, or various XML representations. In this exercise, we will use SPARQL and XQuery to search for data in our triple store. We will construct a SPARQL query first, and then use the same query to search using MarkLogic's Semantic XQuery functions. During this interactive section, you will be asked to click on screen elements, enter text, or type commands into the command line. You may skip steps by clicking on the Forward button. Click the button to begin. We have started MarkLogic's query console on port 8000. In the content source, point to the triples database. Click on the content source drop-down arrow. Select triples, /n:/. From the click on the query type drop-down. Select SPARQL from the list. A SPARQL query has been copied to the query window buffer for you. Examine the query. The two prefix clauses create a db: shortcut to the dbpedia.org resource IRI, and the onto: shortcut refers to the IRI for the dbpedia.org ontology. We are selecting all subjects representing people that were born in Brooklyn. Click the Run Query button to see the results. The results are displayed at the bottom. Press the Enter key to continue. Now replace db:/Brooklyn with db:/Glasgow to change the query. Type db:/Glasgow after the predicate onto:/birthplace, then press the Enter key. Click the Run Query button to see the results. The results change to display the people in our triple store that were born in Glasgow. Now, let's do the same queries, except using an XQuery function to send the SPARQL query. Press the Enter key to continue. We have copied an XQuery function to the query console buffer. Examine the code and note the SPARQL query previously used is the same, except it is now a string being passed as an argument to the sum:/SPARQL function. Select the query type dropdown. Select XQuery from the list of items. Click the Run Query button to see the results. You can see that we are passing the same SPARQL query to the sum:/SPARQL XQuery function. Therefore, we get the same results. Again, in the string containing the SPARQL query, change the db:/Brooklyn object to db:/Glasgow. Type db:/Glasgow, then press the Enter key. Click the Run Query button to see the results. The results change to again display the people who were born in Glasgow. You have successfully completed this task. Press the Enter key to continue. In this tutorial, you learned how to describe semantic data, describe RDF and triple stores, create a MarkLogic triple store and enable triples indexing, use MarkLogic Content Pump to load triple data, use SPARQL to query graph data, use MarkLogic's Semantic XQuery functions to query triples. Congratulations! You have successfully completed this tutorial. Please click on the Mark Complete button to exit this tutorial and receive credit for completing this training.